Hey guys, so today what we're going to be going over is something called implicit differentiation. Now we're coming close to the end of the semester, and I'm going to say out of everything we're doing this semester, this is probably the most complicated thing. This and the next chapter, which is related rates, can be very confusing, but if we stay focused, we'll get through it, so don't worry. All right, let's look at the first thing we have to look at. I want you guys to understand that there's really two ways that we can express a function or an expression. So here's the first one. Something called an equation can be written in explicit form. So what does explicit form mean? It means that y is explicitly expressed in terms of x. So let's look at our first example right here. We have y equals 2x plus 1. We clearly know what y is equal to. It is explicitly expressed in terms of y, in terms of x. There's no confusion here. So y is equal to 2x plus 1. If we take the derivative of this function, it's just 2 because it's linear. It has a slope of 2, so that means the slope of the tangent is also 2. Let's look at this guy now. Well, we have y equals this whole mess right here, x cubed plus 2x minus 1. Again, this expression is clearly telling us that y is equal to some manipulations of x's, okay? So it's explicitly telling us how y is related to x. So what we're going to do now is we're going to also take the derivative of this guy. And you guys know how to do the power rule by now. Just drop this guy down, take 1 away from it, you'll get 3x squared. And then same thing here, power rule again, you'll get 2. So the derivative of the above function is 3x squared plus 2. All right, so now let's look at the other form of our expressions. Something can also be expressed implicitly. So what does that mean? That means y is written in a way that's not so clear, but it's implied to be a function of x. So what does that mean? Let's take a look at this. First example, we have x times y equals 2. So we don't have an expression where it says y equals something. We don't have something that just says y equals something. We have x times y equals something. So because it's not y equals something, we say it's written implicitly. There is a relationship between x and y, but it's not clearly written in this sentence. But guess what? We can always go back to an explicit form, right? How do I get y by itself here? Well, I just divide by x. So I have y equals 2 divided by x. And we can do this as long as x is not 0, because we can't be divided by any 0, right? So look, we went from an implicit form to an explicit form just by dividing by x and restricting our domain. So again, we had to figure out what the derivative of this guy is. So again, we're going to use the power rule. Let's see, equals. Well, how should we do this? We'll say equals dx of 2 times x to the minus 1. So I drop the exponent, so that's a minus 2 x, and I take 1 away from minus 1, so I get a minus 2 on top. So that means the derivative of this guy is equal to negative 2 over x squared. And hopefully this is a review for all you guys. Shouldn't be too bad. All right, let's look at our next example. Remember, we're looking at expressions that are written implicitly, right? They're implied to be, where y is implied to be a function of x. All right, so the next one, we have something like this. We have 3 equals 2y plus xy minus x. So it's a little bit of a mess, but let's see if we can rewrite it into an explicit form, okay? The first thing I'm going to probably do here is factor out this y. So 2 plus x minus x equals 3. Then what I'll do is I'll get rid of this x, and then I'll probably divide by this term. So I'll have 3 plus x divided by 2 plus x equals y. And there we go. Again, we have now gone from an implicit form to an explicit form by just doing some algebra, okay? And maybe we'll have to change our domain, right? So right now, x can't equal minus 2 because then we'll get a 0 in the denominator. Okay, so what is the derivative of this guy? We're not going to do it on this page because it's going to take too long. And you guys know if you have a fraction like this, you got to use the quotient rule. And if you do it right, you'll get this answer. -5 over x plus 2 squared. Okay, where's my last example? There it is. Okay, so here's our last example. We have x squared plus y squared equals 9. So let's go ahead, where it's written right now in implicit form. Let's go to explicit form. So the first thing I'll do is I'll take away this x squared. I'll have y squared equals 9 minus x squared. I have to undo this square, so I'll take the square root of both sides. When I take the square root of a square, don't forget, we always do plus or minus, right? Plus or minus. So what do we have at the end? We have y equals plus or minus square root of 9 minus x squared. Now, we have a problem here, and hopefully a lot of you see the problem. The problem here is that this guy, when we rewrite this guy in terms of y in explicit form, we don't have a function anymore. Why do we not have a function? In order for an expression to be a function, it has to clear the vertical line test, meaning one x value can't go to two y values. So let's pretend like we're plugging in x equals square root of 5. Maybe I should rewrite this. So if I plug in square root of 5 into this guy, so if I put square root of 5 in here, good, then I get plus or minus square root of 9 minus 5, and that's just the square root of 4. So that means if I plug in square root of 5 for x, my answer will be -2 and 2. So if I were to graph it, it would look like this. When x is square root of 5, I get 2 and I get -2. But guess what? This fails the vertical line test, right? If it fails the vertical line test, it is not a function. So we can't really differentiate this guy because he's not a function. So the question is, what do we do? How do we still find dy dx? Okay, that is our goal. We're still trying to find what dy dx is, but we can't really differentiate something that's not a function. So what we do instead is we use something called implicit differentiation. We're finding the derivative of a expression in implicit form. So when do we use implicit differentiation? Well, we use it on equations that aren't functions. So in a way, we can't write y as a function of x. And we use implicit differentiation when y is an implied function of x. So you'll see what I mean once we do our examples, okay? All right, so before we start even doing any implicit differentiation, I want to go back to just normal differentiation. And I did this in class this is how I showed you originally how to differentiate. I'm just going to review it real quick. So we're looking at this example. So I have a function 2x plus 1, it's a line. And what I'm going to do is I'm going to find the derivative, right? I'm going to find the smallest slope possible, if you want, the smallest rise over the smallest run. So what do is I attach d dx to both sides. And on the right hand side, what happens is I kind of distribute this d dx into both of these terms. They're split by a plus sign, so I'm going through both of these terms. So I have d dx of 2x, and then I have d dx of 1. Of course, the derivative of a constant is just, oh, sorry, before we even get there, sorry, I forgot the point of doing this. So you want to think about it like this. What we're doing is we're splitting these guys up into two terms, 2x and 1. And you want to think about, we're differentiating each guy and just pretending they're each their own function. Meaning I'm just pretending at this step right here that I'm differentiating only a function g of x, where g of x is equal to 2x. And in this step right here, I'm pretending like the only function I have is h of x, where h of x is equal to 1. So even though I'm differentiating f of x, I'm kind of splitting them up into two parts, into g of x and h of x. So they're kind of all connected like this. All right, so if I differentiate g of x, I get 2. And if I differentiate h of x, I get 0. And obviously 2 plus 0 is 2. So we're good, we're golden. So I hope you guys remember that's how I first showed how to differentiate. Of course, now when we do it, we have shortcuts. But this is kind of what's happening in the background of our mind, hopefully. Okay, so we're going to use this same approach, this guy right here, when we first learn about implicit differentiation. So let's go ahead and look at that. So we have a function written in implicit form, and we want to find what dy dx is. So we're not going to try to go to explicit form or anything right here. We're just going to d dx each side, okay? So just like how I distributed, see how I distributed the d dx at this step right here? Let me get rid of some of these arrows because it's kind of crazy. See, at this step, what I did was I distributed the d dx at this step. That's the same thing I'm doing right here. I'm distributing this d dx across all terms. So I have d dx of x squared, d dx of y squared equals d dx of 9. So this term and this term are very easy to do. We know how to do this, all right? The derivative of a constant is just 0, and the derivative of x squared is just 2x. We know how to do this. But the real problem is this guy in the middle. What you're going to do here is you're going to rewrite y as a function of x. Because in order to do implicit differentiation, sorry, come on computer, y must be an implied function of x. Okay, and just like what we did here, where we're thinking about this term or these terms as functions of x, different functions of x, that's what we're doing with y, right? We're thinking about y as some function of x. So we have not just y squared, we have y of x squared. And we want to take d dx of that. Now, before we move on to the next step, I want you guys to remember what the chain rule looks like, because that's what we're going to do next. Remember what the chain rule says. If you take the derivative of some function g of x to the nth power, you drop the you drop the exponent, take one away from it, and keep that inside function exactly the same. However, then you have to multiply your entire function, your result, by the derivative of the inside function. So here's an example. I'm taking d dx of 3x plus 1. I'm going to drop n down. So this guy's n. This is n minus 1. And this guy is g prime of x. Right? Because the derivative of 3x plus 1 is just 3. So hopefully you guys can see that. Hopefully you guys looked at my chain rule episode and then it makes a little bit more sense. So this is what we're doing here. Okay. So when we're differentiating y of x squared, we're going to use chain rule. So this is n minus 1. This guy right here is g of x. And now I'm multiplying it by this guy right here, g prime of x. I'm using g because I'm referencing this this formula that I gave you. Okay, I know it is y, but I'm just trying to reference this formula that we just used. So look right here, we use the chain rule. I drop the numerator, I say that every single time. I drop the exponent down, I take one away from it, and I multiply it by the derivative of the inside. Now we don't know what y really looks like, okay? We don't. Sorry, I just totally messed up, didn't I? Huh. There we go. Well, so I don't know what the function y looks like expressed as x, but I know that dy dx is just dy dx. Okay, I know the derivative can be written like this. All right, so then I continue. So I have 2x plus everything we have on top equaling 0. So remember the original question, I'm trying to find dy dx. And I have a dy dx right here. All I'm going to do now is I'm going to use some algebra to solve for dy dx. So the first thing I do is I get rid of this 2x term, I put it on the other side right here. And then I divide through by y of x. And then that's my answer. So a lot is happening there. Good thing you guys can rewind these videos and really see what's happening. Now, alternatively, this is like, what's working in the background. Just like how this is what's working in the background as we differentiate a linear equation like this. But there's an easier way to think about it. To take the derivative of an implicit, something that's written in implicit form, I want to take the derivative of it. All you have to do is take the same thing, take the derivative of this guy, and then take the derivative of this guy, acting like this y is an x. Okay, so how would I take the derivative of x squared? It would just be 2x, right? I'm pretending like y is like x, and I just differentiate him the same way. But then what I do is I attach a dy dx next to him. See this dy dx? So I differentiate everything normally, like everything is an x. But anytime I differentiate a y term, I just add this, I multiply it by a dy dx. So this guy differentiates into this. This guy differentiates this. A constant goes to 0. And I just do some algebra to figure out what dy dx is equal to. All right, guys, we'll do a couple more examples in the next video. I'll see you then.